Hello viewers, in this video I will be explaining the implementation of link state routing algorithm. This is one of the experiment in the Computer Networks Laboratory in the 6th sem of Electronics and Communication Engineering stream under 2017 scheme of VTU. Now let us go through the content of the presentation. We would go through the network scenario, cost matrix, execution steps, TCL script, followed by the simulation and then the result. Before we get into the topic, let us see what is meant by the link state routing algorithm. It is one of the three major protocols for unicast routing. What is unicast routing? Unicast, as the name itself suggests, is the transmission from single sender to a single receiver. It is a point-to-point communication between the sender and the receiver. So, the three major protocols of unicast routing include distance vector routing, link state routing, and the path vector routing. The link state routing is the second family of routing protocols, while the distance vector routers use a distributed algorithm to compute their routing table. Link state routing uses link state routers to exchange the messages that allow each router to learn the entire network topology. Based on this learned topology, each router is then able to compute its routing table by using a shortest path computation, which would be seen in the simulation at the end. The features of the link state routing protocols include link state packet, a small packet that contains the routing information. Second would be the link state database, which would be a collection of information gathered from link state packets, followed by the shortest path first algorithm, that is Dijkstra algorithm, which is a calculation performed on the database results into the shortest path. Then we have the routing table, which is a list of known paths and interfaces. So now let us know how does the shortest path get calculated. The first step would be the node is taken and chosen as a root node of the tree. This creates the tree with a single node and now set the total cost of each node to some value based on the information in link state database. In step 2, the node selects one node among all the nodes not in the tree-like structure which is nearest to the root and adds this to the tree. The shape of the tree then gets changed. The step 3 includes updation of the cost of all the nodes in the tree as the paths may have been changed. The step 4 would be to repeat step 2 and 3 for the node until all the nodes are added into the tree. Now let us look into the network scenario. Let us consider 5 nodes. Let us connect them together. Now let us define the agents at the source and destination. Now that we have used UDP, the null node would be the agent at the destination and N0 would be the source node and N4 would be the destination node. Let us attach them to the source and destination node respectively. Once we are done with this, it is time for us to define the agent application at the source node. Now let us connect the agents at the source and destination. Fine. Now once we are done with this, let us define the cost for the links established between the nodes. Now, let us tabulate these in the form of a matrix. Now, the matrix seen represents the costs between various links. Say the cost between N0 and N1 is 3, N0 and N2 is 1, N3 and N1 is 2, and similarly between N0 and N4 is infinity because there is no link established between the node N0 and N4 as seen in the network scenario. Now, the tasks performed in the TCL script includes create simulator object, open the NAM file, open the trace file, define the finish procedure, define the nodes and label them, establish the link and orient them, set the queue limit, assign the cost to the links, add the agent to the source node, add the agent application, add the agent at the destination node, connect the agent at source and destination, instruct the algorithm to be used, introduce the traffic, and run the simulation. Now, let us open the TCL script to execute all the tasks we had listed in the previous slide. Gedit. I would name the file to be p6.tcl. Press enter. Yes. Now, the first task is to create the simulator object. So set ns, I would name the simulator object to be ns, then new simulator. Now once we are done with creating the simulator object, let us proceed to open the NAM file as well as the trace file. So I would write the command to open NAM and trace file. Now the syntax would be set, tf would be the name I would be giving, and here you can write open p6.tr in write mode, that is represented by w. Now that we have opened the file, let us trace it, or let us tell the simulator object to trace it, and it would be $ns trace -all $tf, and the same I would do for the NAM file. So I just copy it and I name my NAM file to the NF, so I just change this to NF, and here it is NAM, then over here it is N, and yeah, there you go. You have opened the p6.nam NAM file in the write mode, and now ns would be tracing it. Now let us define the finish procedure. Okay, fine. Proc finish. Now, before performing any task, let me declare all the objects which are declared ns, nf, and tf as global. Once I am done with this, let me try to delete in case any content is present before this. So I write flush trace. Now, once I am done with this, since all the work is done, let me close my trace file as well as the NAM file. So the syntax would be close $tf, that is the name given to the trace file object. Similarly, close $nf, that is the name given to the NAM file object. Now once we are done with this, execute nam p6.nam ampersand. Okay, Now the final task would be to exit. There you go. You are done with the job. Now let us move ahead with defining the nodes. Since I have considered 5 nodes, I would be naming them as N0, N1, N2, N3 and N4 as you have seen, and I would be defining it in the format as below. Set N0, then the name of the simulator object, that is NS, and then node. So the same I would replicate for the other 4 times, and I can just say N4, N3, N2 and N1. There you go. You are done with defining all the 5 nodes. Now let us move ahead with defining the links between these nodes. So define the link. So defining the link would be very simple. So I would refer the simulator object, then duplex link would be the type of it, then the link is to be established between the nodes N0 and the node N1. Then I would set the bandwidth to be 100 MB followed by 10 milliseconds of propagation delay, and the queue type would be drop tail. Once we are done with this, let us move ahead in setting the queue limit. And again, the format is queue limit $N0 and $N1 because that is where the link is established. So I set the queue limit to be 50. Okay, once we are done with this, let us copy and replicate as many number of times as we want the links. Okay, so I want the link to be established between N0 and N1, N0 and N2, N0 and N3. Hence, I replicate it thrice. Okay, so now let us just edit it appropriately. N0 and N2, then N0 and N3. Fine. Now that we are done with establishing between N0 and N1, N0 and N2, N0 and N3, let us move ahead and establish the link between N1 and N2 and N1 and N3. So I replicate the same for 2 more times, and it would be N1 over here, and over here I'll write N3, here I'll write N2. Okay, once we are done with this, let us establish a link between N2 and N3. So I replicate it once more, and there you go, N2 and N3. Here also the same thing. Okay, now once we are done with N2 and N3, let us move ahead with N3 and N4. So I just replicate it once again, and I just change the names of the nodes over here, N4, and I leave the rest of the variables like the bandwidth and the propagation delay and also the type of the queue and the queue limit to be same. Fine. Now that we are done with establishing the links and setting the queue limits for them, let us move ahead with orienting these links. Now, orienting links is again in a proper format, that is $NS. The type of the link is duplex link, hyphen OP, which represents option, then $N0 to $N1. That is, I'm referring to the link between N0 and N1. Then I say orient right. Okay, orient right. Once done, what I can do is I'll just copy it and I'll orient all the links which I have defined above. So I have defined 7 links. So I just duplicate it 7 times and there you go. I'm done. Okay, fine. Now that we are done with listing out, let us edit it appropriately. So I know that the link is between N1 and N2 and N3. Then one more link between N2 and N3. Then the last link between N3 and N4. So now I want the link between N0 and N1 to be oriented right, and the link between N0 and N2 to be oriented right down, and the link between N2 and N3 to be oriented right again. So I retain this as well. Then the link between N1 and N3 to be oriented left down. So I just change it to left hyphen down. Then I want even the link between N3 and N4 to be oriented left down. So I just change it. Followed by the link between N0 and N3 to be oriented right down. So I just change it here. Okay, fine. Now we are left with one last link to be edited, that is the link between N1 and N2 left hyphen down. Okay, once we are done with defining the links, orienting them, let us proceed in allotting or assigning the cost to the links established between these nodes. These costs, as I have mentioned before, would act like the priorities which will be preferred when the transmission of data packets are happening in the network. So I'll write the command to be assign the cost. Okay, so the format would be very simple, $cost. The node would be between N0 and N1, and I assign the cost to be 2. So I just copy the format, and since N0 is connected to N1, N2 and N3, I replicate it 2 more times. Okay, so this is 2 and this is 3, and I can set the cost to be 1 here and 3 over here. Now once I'm done with this, let us move ahead and set the cost for the remaining links. So it would be, I just replicate it and I just change this to N1, and the remaining nodes would be N0. Since they are duplex link, the transmission can happen on either ways. So therefore I'm assigning the cost in either ways, that is from N0 to N1 and in the reverse order as well. So I just copy this and replicate it thrice. Okay, fine. Now the cost I would assign here is 2, 2 and 3. Okay, so this is between N1 and N0, N1 and N2, N1 and N3. Okay, fine. Now between N2 and N1, let us edit it, N2 and N1. Now I would assign 2 to be the cost of this. Then for the other 2, I would assign 0 and 3, and the cost I would assign would be 1 and 1. Fine. Now that I'm done with this, let us move ahead and assign the cost for the links in which the node N3 is present. So the format again remains the same. It is N3, okay, N3 and N1, for which I would be assigning 3. Then I just copy it, okay, fine. Now N3 and N1 I'm done, N3 and N2, for which I have the cost to be 1. Then N3 and N0, for which I have the cost to be 3. Then the last one, N3 and N4, for which I have the cost to be 2. Now the last node, that is N4 to N3, I assign the cost to be 2. There you go. I'm done with assigning all the costs. Now let us proceed to create the agent at the source and the destination. So I just write the comment agent at source and destination. Now the agent I have decided to attach is UDP, so I just name it as UDP0, and then here you can just write new agent slash UDP, then $ns attach hyphen agent. Then I wish to connect it to my source node, that is N0. So I just say N0 followed by the object of the agent at the source, that is UDP0. Once I am done with this, let us create the object for the destination node, that is N4. So the destination node would be connected to the agent null because we have used UDP, that is user datagram protocol. Null1 would be the name I would be giving it, followed by new agent slash null. Now once I'm done with this, let us move ahead and attach it to the destination node, that is N4. $ns attach hyphen agent $n4 null1. Now let us connect the agents at source and destination, that is $ns connect the object of the agent at the source, that is UDP0, followed by the object of the agent at the destination, that is null1. Fine. Once we are done with this, let us define some of the parameters, that is the packet size. Say $UDP0, which is the object of the agent at the source, set packet size to be 1500. Fine. Now that we are done with this, let us define and set up the agent application, that is CBR. Since we are using UDP, we are bound to use CBR, that is constant bit rate. So I just write a comment, set up CBR, okay. Now set CBR0, and here I would say new application slash traffic slash CBR. Okay, so once I am done with this, now let us attach the created object of the agent application to the agent at the source. So I says $CBR0 attach hyphen agent $UDP0. Now let us define the parameters like packet size, rate and random, and I would write $CBR0 set packet size to be 1000. Then I would set the rate to be around 1 MB. Okay, once I am done with this, now let us set up even the random $CBR0 set random null. So why am I setting null? The packet size and rate are pretty self-explanatory, but random isn't. It looks though, isn't it? So let us see why random is necessary. The role of it is to decide whether or not to introduce random noise in scheduled departure time. Okay, so once I'm done with this, then $NS at 1, that is time, when time is 1, I wish to start the CBR and I wish to stop it at 5. So at 1 it starts emitting the packets, at 5 it stops. Now once we are done with this, it is time for us to implement our main aim, that is link state routing algorithm. So how do I specify it? Is very simple. $NS RT proto, then link state, that is LS. Okay, now the last but not the least, $NS at 5, I would call the finish procedure, and then $NS run, which would run the simulator. Now that we are done with typing all the tasks performed, now that we are done with performing all the tasks which we had listed out, let us move ahead and see the animation. So I just write ns p6.tcl. Fine. Now we are good to go and watch the simulation. So I'll just click on start. I'll speed up a bit. There you go. You can see the packet movement from N0 to N4 through N2 and N3. So we have successfully implemented and simulated the link state routing algorithm, and we have verified that the shortest path from N0 to N4 is 0, 2, 3 and 4. Now that we have seen the implementation of the link state algorithm and also have simulated, let us have the questions, in case any, in the comment section below. And if you don't have it, thank you for patient listening.